Pew! Yeah, PhotonicDrive. So by the end of the video, you guys will understand why I named it that. I am having a little fun, but it is honest as well. So welcome, everybody. Thank you for joining me again. This video is a little long, so we're going to do it in 3 acts. So this will be Act 1. Until recently, I have been doing speed regulation using feedback from a Hall sensor and the magnet poles that are on the bottom of the platter. And sometimes it works really, really well. Sometimes you can see what happens right here. I get a little drift, so, I'm pointing it out. Sometimes those lines walk a little bit right. Sometimes they walk a little bit left. In general, they are pretty solid, but it's not as stable as I'd like. So right now, I am actually applying some drag, and I'm testing to see how things are working when I'm actually giving some resistance. So again, lines are pretty solid, but there's some walking that I don't like, and it didn't always react as quickly as I wanted. But after a lot of research and a lot of hard work, you can see that I'm now applying some really good feedback and getting good results. Let me show you how I got here. I decided to first take apart and reverse engineer the motor controller that I was using. This thing does not do speed regulation. It's just a motor controller, so it takes either PWM, or if you remove the potentiometer, it will take an actual voltage. So I can supply voltage from a DAC, or I can do PWM from a microcontroller. Either way, by studying the traces and the chips on the board, I was able to put together a pretty good idea as to how it was working. And then I went ahead and I studied the schematic again, because I've looked at this many times, but now I actually really understand what's going on under the hood on each one of those proprietary ICs. So, the chip that you see bottom left, the chip that you see on the right, the bigger one, the one that's on the next page, actually know what they're all doing, including what the quad NAND gate in the upper left is doing. And so over here, that chip, for instance, is the actual motor driver. So it's the equivalent of what you saw me reverse engineering in that motor controller that I've been using. And then my actual speed regulation logic is sort of the equivalent of some of the stuff that was on the previous page. So the stuff on the top, I'll go over a bit later, but that's how they're processing feedback. This is what the actual magnet pole and coil configuration looks like for the SL1200, if you're curious. And it was selected because of the information that you see on screen right now. So this is something I learned about recently, as well as cogging positions and winding ratios. So James K. Roberts, who's that? Well, before we go any further in explaining things that I was researching, I'm going to just mention this guy, because this video series that you see right here, and I will link it in the description, man, it was just invaluable information. The way that he speaks is awesome. It's reminiscent of, maybe 50s or something, but also just his vast knowledge and the way that he expresses things is just great. Also, Dr. Santanu Chaudhary, this guy, as you can see from the picture, probably has a very limited sense of humor while he's teaching. It's part of these NPTEL series of videos, which again, I will link in the description. But these were also not just for this PLL stuff. There was only one video of his for PLL, really, but just microcontroller stuff. Man, he is very good. He knows his stuff, and it's no nonsense. It's all practical, and unlike some other academic, lectures where you get sort of theoretical. His is all knowledge that you really need, and it's all practically presented. Same with James K. Roberts. Like, his course on feedback systems is just amazing. So, man, I did research, and as you can see, I did a lot of research. I looked at all sorts of things, first of all, just trying to identify what was going on the Technics 1200 schematic, because they don't obviously supply information to the public about their own proprietary chips. So, just trying to look at that and figure out what they were doing under the hood in order to, start to understand how I would like to make my own system that would be analog instead of microcontroller processed. Right now I'm using an Arduino to process the feedback data I get from the Hall sensor, the extra Hall sensor. But number one, the number of poles that I have in my magnet array, that defines, how many samples I get per rotation. Even with additional sample points per rotation, doing this in a microcontroller is really not the best approach. You're going to have latencies that you just won't have if you're doing this with analog circuitry, specifically negative summing feedback with a drive signal via an op amp. So that's the basic approach. But there are also more refined ways that you can do this sort of thing. So there's what's called monolithic analog feedback closed loop system. There's also something else that I will go over towards the end of the video in Act 3. And now a quick word from our sponsors. Do you know why Bob is forlorn? Well, let me tell you about it. In fact, not just Bob, but do you know why Tyler and Bob are really, really just looking forward to something here? Forlorn, and in fact, Tyler's mad. Tyler's mad, and do you know why Tyler's mad? Do you want to make these guys happy? Look at that face. You want to make him happy, right? I want to make him happy. And what would make this guy happy is for everybody that watches my videos to please get me to monetization. The would be 1,000 subscribers and 4,000 watched hours. So please continue to watch my videos. Please also do subscribe. And there is actually, there's a carrot at the end of this stick. So I have explained in prior videos that once I reach monetization, I will show you guys everything about my BLDC motor. Right now, I'm showing you quite a lot of good stuff. So anybody that's out there that's interested in this sort of thing, yeah, this is obviously, you're going to be like, wow, this is a really great in-depth video, and this gives me a lot of ideas. Well, do you want all the ideas? Get me to monetization and I will show you guys some pretty amazing stuff, and I will fill in the rest of the gaps. Okay, so now for the depressing part. Yeah, I'm going to try really hard not to cry. My kitty cat Tyler is now approaching 19 years old, and he has appeared in a bunch of my videos, since the first ones I've really posted on YouTube here in one way or another. He's obviously a part of my heart. So, his health has been declining, and I think that this is the last video that he's gonna appear in. I'm gonna miss him so much. Okay, I gotta go cry now. So this is the top right of the second page of the schematic for Technics 1200 Turntable. I've looked at the schematics before, but this time around I really wanted to, reverse engineer their approach, and so I decided the best thing to do would be to start with feedback. How are they, taking it in and processing it and then applying it? So that's what you see right there, is the bit of circuitry that actually is a precision amplifier and filter for the feedback. And if you've ever pulled the platter off of a Technics turntable, you'll see something that sort of looks like that. It's a copper what I'm going to call a squared serpentine pattern. I did not get that one very squared. That's the first one that I made in just a little section. That's the second one. And I just wound some enameled wire around a long, thin, rectangular piece of plastic, a bit of print, a 3D print. So I wrapped it around there, and then I pulled that plastic part out and I unfurrowed the coil. And as I was unfurrowing each turn, I was sort of twisting it one way or another, and that got it to be, what I'm going to call a flattened coil. And then I used my manual arbor press to flatten it out a bit, put that underneath the platter, as you see right there. I actually just taped it down to the plinth, and the magnet array moves over it. And you can see I'm got a little bit of circuitry right there that's processing the input from that, which is literally what's called a pickup. A lot of motor systems will just refer to this as a pickup or a magnetic reluctance tachometer system. So I went ahead and I built out the same circuit for processing feedback as in the schematic for the 1200, and tried using that little bit of flattened coil that I made. This is actually the first one, so it's just a small section. And even with the larger second one that I made, it just wasn't the best. There's a lot of issues with doing it this way. You get a lot of interference that you have to deal with. Even if you filter, it's still sort of affecting the wave. So I decided, okay, let's take another approach. And I thought about it for a while, and I said, okay, the best thing for me to do is probably do a rotary encoder. So that's what you're seeing is sort of the first version of that. And now I've plugged in the rotary encoded data to the microcontroller software. So it's now taking the data from that sensor, which was a photo. I'm trying to remember if it was that original was a photoresistor, and I was using a laser diode that I just pulled out of a $5 laser pointer. I fancy it up in a second, so you'll see that. But that's not bad. That's super clean feedback in comparison to using a pickup, which is essentially an antenna. So now you can see a later version. So I've actually got a laser diode that I purchased from an electronics store out here, and instead of a photoresistor, I'm using a phototransistor now. And I'm getting, again, nice output, but this time extremely accurate. It's not only a nice waveform, but it's also very, very precise. And also completely free and clear of any other interferences because it's light-based, right? So that's why I called it PhotonicDrive. Also, since my turntable bearing floats, it's a magnetic bearing. There is no metal-on-metal coupling at the bottom of the rotor shaft. And that presented a challenge for doing this, because where you would put the light source and the actual sensor, and then the disc in between, that disc in between moves. So you have to space those out. And so that's why I used a laser, because that gives me really accurate data on the other side of that disc, even if the light source itself, the laser, and the phototransistor are separated by a good distance to allow my encoder disc to freely move up and down. So that's the actual phototransistor that I ended up going with. It doesn't have a base because it's internal. The base is actually the photo element itself. That's the actual diode that I went with, just because it's so small, and it does actually have an internal lens. It's not adjustable, so that was kind of something to deal with. But even though it's not adjustable, it still stayed coherent for the length that I needed, the distance that I needed. So you can see right there, I actually made a disc that has more teeth in it. So that's kind of the second or third disc I made. The final one has enough teeth such that it gives me the exact same feedback that the Technics turntable does. So that magnetic pickup, if you look at the schematic, clearly states at 33 you're going to get a 50 hertz signal for feedback, and that would be 20 millisecond period cycle. So I implemented an encoder disk that gives the exact same amount, the same values for feedback. I put a lot of work in on the feedback hardware and circuitry because without good feedback, you may as well not apply it. Okay, I've got the new laser and sensor and circuitry hooked up, and it's making the computer happy. The other setup was not giving proper input to the computer. That's the circuitry, so that's a lot simpler than what I had before. And we're getting really nice feedback that actually matches the drift that's going on. So it should be 20 milliseconds and 50 hertz. And those are nice square waves. And every time there's drift, like right now, you're seeing those bars move to the left and to the left. Every time that happens, it's registering faster. So right now, you see it's going faster, slower, and then faster and slower. And faster, in a second it'll be 53, yep, quick. So there you go. I'll turn this into voltage and negative summit now, and it should correct. So this has absolutely nothing to do with what I'm trying to actually achieve. I am getting feedback right now from the turntable, so is my app, so is that LED, and you can see on screen what it's looking like, and the frequency, and all that. I'm trying to turn that into a voltage that represents the frequency, right? So just a solid voltage. And I tried a circuit that's not working. But what's interesting is with different capacitor values for that green cap, when I change it out to other values, and then I adjust this pot, I get some really cool shit to happen. Here, I'll do it right now. Ooh, look at that. So from the same wave, from this one, so I'm almost doing sort of a PLL, but in analog circuitry. So you can see I'm taking this one carrier wave, and now I've just added 2 more pulses in the downtime. So let me go back to the original, and then whoop, and then I can do this. Yeah, buddy. So I could just keep adding. So that'd be like 3. You can see peeking in 3, and now other caps do other things. So here, let's try this one. I don't know what this one's gonna do. Oops. You go in there, and you go in there. Oh, that just makes the phase wider. See that? It's like trying to fake data. It's pulling the phase wider. The on phase, that's interesting. Let me go back to this guy. So this is a different mylar. Before I was doing a 1UF electrolytic, and it was widening the phase. This one more easily gives me that third than the other one. And then both of them do this bar, which is interesting. So this is almost like a clock. Not really doubler, but sure changing the initial input signal. So what's cool is a lot of the stuff I've been doing and figuring out, I could make some really cool synths with this actually. Especially the circuitry I figured out up here to clean up the sensor input. I was actually shaping the waveform. Okay, so I've now accidentally created a VCO. This is now a pretty constant square wave, and this will change the frequency when I turn it. Oops, hold on. Yeah, buddy. It does sort of fall apart here, so it's not perfect or anything, but within a certain band, frequency band, and probably I could go higher if I had a different value pot on here. It's kind of cool. I didn't mean to do this, but I did. That's pretty solid. No, that's not taking any input, that's just generating it on its own. So it's not what I want, but that's interesting. Is turning that square wave into a nice voltage. Right now it's 2.9 volts, so I'm not even going to have to offset this or gain it, I don't think. Well, possibly I'll have to offset it actually. Because when it goes to 0, I still want it to have some DC offsets, so I need to offset the output. But it's very responsive, so if I just put a little pressure on, you can see that that just rippled, and a lot of pressure on. It's pretty responsive. I think that it's going to be good. So if I DC offset this and buffer it, and then buffer the input from the DAC, and then negative sum, I should be golden. Okay, ladies and gentlemen, Act 3. And in Act 3, we are going to actually do something with this feedback. So now that I have played around with their system, thought about it, created my own system, fine-tuned actual circuitry that's taking in the initial signal and then doing something that's what's called differentiation, to that signal, then starting to build out an actual processing chain that will take that feedback and apply it to the drive signal and actually get some self-correction in real time. So let's take a look at that. My feedback, and it's coming in really nice right now. That is seemingly very accurate. And so what I've done is you can see that the software is now just the software. I'm not even through analog circuitry, but just my software is regulating the speed based on, and it's making a totally different noise, which is interesting. I'm actually applying feedback, like moving a little bit. I need to adjust it, but at least it's actually applying feedback. So if I put pressure on it, it should actually adjust, and that's what it's doing. It's actually adjusting. If I put a lot of pressure on, yeah, dude, it's actually adjusting. So if I do this and the computer simultaneously, I should have perfect speed control. And then if I take off, it should stabilize again. Yeah, pretty much. So this and the computer should be perfect. So I've got both the computer and the feedback going. Not everything is perfect setting wise, but that's great. Look at that. Put my finger on it right now, and those are solid. They're moving a little bit, but it's reacting great. That's fantastic. I just need to fuck with some settings, but this approach is actually working, which means I can move on to the PLL, which should make everything perfect. I've actually achieved feedback, analog feedback, good analog feedback. Look at that. Yes, dude, yes! Fuck yes. Bobby, you get it. He's like, dude, I don't care, man. I love you, Doug. Oh, that's so great. Wow. Wow. Fantastic. It's funny, it's making a totally different noise now, but whatever, I don't care. It's great. Look at how quick it responds now. Wow. Also, like from dead stop, it'll go to speed really quick, so stopped. Boom. We're so close. very close, man. I just need to fine tune some stuff. But just this alone. Oh my god. That's what we've been looking for forever. Holy cow, that's so great. Alright, we've now reached the end of Act 3. PLL. What's PLL? Well, that's phase locked loop. And that's how the Technics turntable works. You take a very accurate signal generated by a quartz crystal and you modulate it with another signal, which would be the feedback, and you do this in a way that uses what's called a phase frequency detector, as well as a NAND gate, which is what you're kind of seeing in the images there. And so that's what I am working on now. So next video, you're going to see this entire system working on a phase locked loop. I think you're all going to be very interested to see that video. So please subscribe. Help me help you to continue to be inspired. Help me help you guys to get some shortcuts to, this stuff and make it accessible. Let me do the hard work. So I will see you all next time. Please take care of yourselves and be kind to others. Namaskar.